Thank you. It's a pleasure to be here today. And it's an honor to be asked to present the work on behalf of my team, Jim Sears, Rodrigo Sotero, Jeff Amirian, and thanks to Rob Martinson and Chris Luchin for their supports, loaning us an AFX laser and giving us a lot of technical contribution to help us through this project. So what we're here to do today, well, I'm here to talk endlessly about metal additive manufacturing. You all showed up to see the previous presentation, but you're sticking around to listen to me, and I appreciate that. So a quick review of laser powder bed fusion, which is the modality that we're here to talk about. There is a process chamber. It usually has a non-oxidizing atmosphere in it, in the form of a vacuum or positive pressure inert gas. With lasers, it's usually positive pressure inert gas. There is a powder conveying system, spreads a thin powder layer on the build platform. The platform is scanned by an energy beam, which can be electron beam, a laser beam, alien death ray, something, but there's going to be some beam that's going to be focused, has optics, has scanning, has a lot of complicated contraptions that are making this all possible. In concept, this is all very simple, but the difficulty is in the details. Anyone can print a part that resembles what your customer wants, but to print the part that meets dimensional tolerances, has the right surface finish, is reproducible and repeatable, not only on the same build plate, but build after build after build, month after month after month. And we're doing layers, hundreds of layers, thousands of layers, 10,000 plus layers, builds that last days, weeks, even some go on for months. The biggest challenge is that within this printer, it is an assembly of a lot of complex subsystems that move powder, convey powder, spread powder, heat the platen, move the platen. There's process gas flow, there's process gas filtration, there's the energy source, there's the scanning. All these subsystems have to work together, and they all have to be equally good. Now, we're working with this amazing laser, AFX-1000, 1,000-watt multi-mode laser. It is an amazing tool to work with, but what we're going to find also is that if all the rest of the subsystems aren't as good, it gives us a lot of challenges. And this is what's been at the root of this slow advancement in laser powder bed fusion. We had 1,000-watt lasers years ago, but we couldn't use them. Our scanners didn't have good enough coatings to take that much power. Our lenses heated up and would distort under that much power. We generated so much soot, so condensate and weld spatter that our gas flow system couldn't deal with that. So as we went from like 200 watt to 400 watt and higher, there was always a leap forward in laser power and then a step backwards as one of the subsystems wasn't up to par. And then we'd get that engineered up to everything being equal, and then we do something stupid like put two lasers in there, and now our gas flow problem was doubled. And I'm going to talk about gas flow a lot today, even though we're here to talk about laser. So the process of laser powder bed fusion is very simple. We all did it as children. It's like coloring in the coloring book. The picture is our CAD, and then we go into our crayon box and we'd pull out that really sharp crayon, and we would meticulously draw along the inside of the picture and create the outline. We call that contouring. Then we go back in the crayon box and we pull out a real blunted crayon that has lots of surface area, and we just fill in all the space, going up and down, overlapping our layers, moving from left to right. That's what we're doing in laser powder bed fusion. And we have to do just like in coloring, make sure we get to the line but don't go over the line. Make sure that our hatching, which is the filling, goes to the contour, doesn't go over the contour, doesn't fall short. And where we have gaps, where we would have had those white spaces when we colored, we call that a lack of fusion defect, and that will make a bad part or a good looking part that will fail later in service. And again, gas flow. We're going to keep talking about gas flow. So more sciencey, how this all works. We have our spot size, which we're normally working with about an 80 micron diameter Gaussian spot. We have a fixed spot. It's a good compromise size because it lets us contour with good surface finish, and it lets us print details of pretty good feature resolution down to about a 0.5 millimeter, and it's kind of okay about filling in all the bulk, but having just one spot size that does not fit all applications is a challenge. And we have, as we can see, so the Gaussian spot, which is hot in the middle, middle and cold on the outsides gives us this really deep melt pool, and it's kind of like an inverted bell shape. And as a result of that shape, we have to overlap our traces a lot. And we follow this tool path, scanning up, coming over a little bit, overlapping, scanning down, scanning up, scanning down, constantly overlapping. And the need to overlap a lot is also cutting into our efficiency. We have some other problems that are going to happen, and we'll talk about in a moment. But in terms of how this all works, we can also think about it compared to subtractive manufacturing. We talk about feeds and speeds. In printing, we call it parameters. So the depth of cut in milling is just like our layer thickness in printing. The deeper the cut, the more material we can take away. The thicker our layers that we can print, the more material we can deposit. Our spindle speed addresses how much material we can remove in a given minutes per second, and the laser power lets us deposit more material. Our feed rate, moving the part past the mill, increases productivity, and our scan speed, if we can scan faster, increases productivity. Where the analogy falls apart is that in milling, we can put in a small diameter mill and mill a very fine feature, change to a large diameter mill, and take away a lot of material. On the laser side, we only have one spot. We can't change it historically, but that's what we really want to do. Small spot for fine features, large spot for massive deposition. Traditionally, our printing is in layer thicknesses from about 30 to 60 microns, up to about 500 watts. We have more powerful lasers, but an 80 micron Gaussian spot, if I go over 500 microns, I'm just going to keyhole, drill deep into the metal, create lots of porosity, lots of defects. And if we're sending a lot of power in, we're generating condensate. We're not selectively laser melting. We are selectively laser boiling. We are boiling the metal, generating lots of vapor. It consolidates in the chamber in the form of very fine particles, submicron particles, pyrophoric particles. They are jumping around in the atmosphere. They're causing laser obscuration by getting in the way of the laser beam, which results in defects on the melt bed. And then we're also creating a lot of ejection of molten material, weld spatter. And as that jumps out of the melt pool, it coalesces into a very large ball with a gas pore in the middle, drops back down on the bed, and we might weld it in, we might not weld it in. It's kind of big, and it's going to have a void in the middle of it. So this all generates a lot of defects. We can, from productivity, we deposit between about 15 and 30 cc's per hour, nominally around 20. We'd like to be more productive, and that's always our goal, why we want to put more laser power in. So what do we want? We want higher productivity, more laser power, and a variable spot size. So Wayne King did a lot of seminal research in what's really happening when the laser hits the powder, and we saw some earlier presentations today as his work has been taken on by a lot of researchers around the world. We used to think that the laser hit the powder, heated the powder, melted the powder, consolidated it, and then the melt pool would draw in additional powder around it. Turns out the beam hits the powder and pretty much blows the powder out of its way. Imagine the floor was covered in ping pong balls and we hit it with a fire hose. All the balls scatter. The laser is really engaging the substrate below the powder, melting that, and then drawing a bunch of powder in around it. And then it advances, leaving cooling behind it and generating, again, the melt vapor, which is bouncing around up in the chamber. Hopefully the gas flow is taking it towards the vent, hopefully, and is creating weld spatter, which can jump either behind the laser or in front of the laser. We want to get all that stuff out of there. We don't want to generate it at all, but we want to be able to get it out of there. And we can make all these keyhole porosity with this Gaussian spot, and we want to avoid that. So we had been printing or trying to print a part at Amaero for a customer. It was an H-13 tool steel. Most people think that is an unprintable material because it's very crack prone, and it's crack prone because it does not like extreme thermal gradients. But think about printing. We take warm powder, convert it to boiling metal, and then back to consolidated hot metal in like 1 second. That's a very extreme thermal gradient. So how do you print H-13? Well, you increase your plate heating to its maximum potential, about 200 C, spread very thin layers of powder, 30 micron, pour in a lot of laser power, which means we're generating a lot of vapor, and then you scan very slowly so that it doesn't cool off quickly, and that's how we reduce the thermal gradient. So we generated a lot of condensates, and we created horrible productivity. We're scanning at like 600 millimeters a second, which is half of a normal scan speed. You do that, and you can create really nice-looking H-13 microstructure. But as we're printing this part, and it was a very large surface area in this machine, it was almost over half of this build plate, 250 by 500 millimeters. And about 15 millimeters into it, we realized that just the volume of vapor we generated was going to overwhelm our filter. That about 20% into this build, we were going to clog the filter and we were done. So we never got to print the part, but it drove us to, what about this ring mode laser? What can that do for us? And we got an opportunity to simply pull a laser out of one side of our machine and put the AFX in. So this is what happens when you put the beam profiler under it. We get in mode 0 a more traditional Gaussian spot, and as we go through modes 1 through 6, we get this really interesting ring that's hotter on the outside and a nice cool spot in the middle. And that's going to really help us avoid that whole keyhole process. Now, a smart person probably would have done a DOE, stepping from mode 0 through mode 6. I'm kind of crazy, so I went straight to mode 6 because I wanted to compare. I know how bad my life is in a Gaussian spot. I wanted to know what this ring can do for me because it's 300 microns and it's hot on the outside and cold in the middle. So doing some DOEs, and this is hatching only. We didn't do any contouring. The first DOE, we left a lot of the process conditions alone. 30 micron layers, very slow scanning. And in order to look at the microstructure more easily, we just alternated our layers by 90 degrees. Normally we do a 67-degree rotation, but by alternating 90 degrees, it was easier to look at the microstructure and see what's going on. And also that meant that each layer, because we printed 45, 135, each layer engaged the gas flow at 45 degrees. So every layer was essentially the same process condition. And I mean, just these surface finishes alone, again, a 300 micron ring, no contouring. We got great surface finishes. All that labeling was done with the ring also. And, oh, by the way, H-13 prints file hard. It's Rockwell C53. So all these DOEs, I have file hard steel that I have to section and do metallography on. So on the far left, that's the traditional melt pool that we're used to seeing, these very deep bells. And in the middle here, this is the H-13 in the XZ and the XY view. And what you see are these very, very shallow melt pools. They're not at all the deep pool that we're used to. There's no keyholing that's happening. And it's a nice wide, shallow pool, which means we can widen the hatch spacing. It allowed us to reduce the total laser power because we weren't wasting all this Gaussian power in the middle. So we reduced the laser power, widened our hatch spacing, reduced the condensate generation, lowered the volumetric energy density, and we took, I mean, this was impressive. So H-13 is very unproductive, 7.8 cc's per hour. We got it up under these conditions to 9.7. That's a 24% increase. But I was just so amazed at how well this worked that I had to see how far I could take it. So I've never seen anyone print H-13 thicker than 30 micron layers, so I decided, well, we'll go to 50. What can happen, right? So we did a whole series of DOEs, going faster, pouring more power in, scanning thicker, scanning faster. So I've never seen anyone who could print H-13 at high scan speeds because it wants to crack. So at 50 micron layers, 800 watts, 160 micron hatch spacing, mode 6 ring, scanning at nearly 1600 cc's per second, we were depositing at 45 cc's an hour. That was 7 times more than we were depositing before. And that's almost twice what we consider a productive amount of deposition, even in a friendly alloy. but my dear friend gas flow and gas filtration. So we reduced the amount of condensate generation by about 50%, condensate per unit volume of deposited material. But we deposited 7 times the volume per unit time, so we increased the total condensate in our chamber by 3.5 times, which means my dear friend gas flow and gas filtration let me down. And this is why the rest of the subsystems have to catch up with the laser. So in this particular DOE, as we were getting very aggressive with our parameters, in the top left cube was the less aggressive parameter, the bottom right cube is the more aggressive, so it should have been from good to less good as you work your way down. But you notice there's a lot of condensates on the bed, and that's because of a lot of irregularities of the gas flow within the chamber, common problem in laser systems. And so it turned out when I sectioned all of them, they were all full of porosity. That was caused by all this laser obscuration from the condensate, except the one in the bottom corner. That was my most aggressive parameter, but I had good gas flow in that location, so I had beautiful material. I switched to 718 because it's a friendlier material, and I wanted to get crazier with all this printing. So here I'm printing 718 at 80 micron layers. This particular DOE, the volumetric energy is the same for every one of those cubes, but we have low power, low speed on the left, high power, high speed on the right, and an increase in deposition rate from 30 cc's an hour to 51 cc's an hour. Again, like double the normal high deposition rate. And you'll see that the surface finish doesn't look as good as we go from left to right, but that shouldn't fool you in anything. That's all because I'm not contouring, plus my friend gas flow. So if you just calculate this out, this DOE should have been depositing at an average 41 cc's per hour. If you just time it, laser on to laser off, it was actually 37 cc's per hour. And that was because of the jump time from the laser melting one cube to the next cube to the next. Then, if you measure one full layer, scanning time and recoding time, we're now down to 13 cc's an hour because the lasing was 8.5 seconds, but the total layer was 24 seconds. So it took twice the lasing time to do the recoding. And then when you just calculate the whole project out from start to finish based on the whole volume, this project deposited at 12 cc's an hour. So the laser is giving me 41 cc's an hour, but the rest of the subsystems, how they work, how they're programmed, how they've been planned and designed to act as a system, they let me down. They gave me 12 cc's an hour despite the productivity of this laser. And by the way, you would think that the cube on the left has great microstructure and the cube on the right probably's got a bunch of porosity in it. Actually, no. They all look fantastic because this gentle ring, this hot on the outside, cold in the middle, nice gentle ring that takes away that Gaussian spot, that takes away that deep keyhole effect, gives us a much broader processing range from our materials. So, what are the benefits that we've observed? We can use the full 1,000 watts of this laser, and I could probably actually use 2,000 watts. I've deposited in layer thicknesses as high as 150 microns. I couldn't get, I'll try, but I think I could get to 300 if my friend's gas flow and filtration will be cooperative with me. We demonstrated greater than 100 cc's an hour. We probably could get to 200 cc's an hour with good gas flow. And again, the gas flow is the problem. Half the condensate, but we're depositing 5 to 10 times the amount of material per unit time, so we're filling the chamber with condensate. Great tool, amazing laser. Here's some parts that were made on the EOS M290 with this laser. There's also an economy machine out there. The folks at Open Additive sell their system with this laser in here. Does phenomenal work, but the rest of the subsystems aren't up to snuff yet to let us fully realize the potential of this system. So thank you. There's my email address, plus the folks at nLIGHT are welcome to give you my contact information if anyone has any questions, and I'll be around all week.